Hello and welcome to Indie the Abyss podcast. My name is Todd Decker, and today I'm here with Jakob. And Jakob, we've had a couple times before, and he's back again. Today we're going to be talking about statistics, and more particularly, I think, the philosophical aspects of statistics. And Jakob, I was thinking that I've tried to, there with these times, 2021 now, there's so much division and controversy and stuff, and I've tried to steer away from all of that with the topics I've gotten into. It's like, let's just talk about interesting things, and it's like, oh, philosophy of statistics, that's not going to be controversial.
Not in the least.
And as I've been getting into it and seeing like the statistics wars that have been going on around it, I'm like, oh no, this is worse.
I was trying to get away from the culture wars and ended up in the statistics wars.
This is like that times 10. So, so I may have to like go into hiding after this and go into a witness protection program or something. But we'll risk it. But anyways, happy to have you on. Thank you.
It's glad to be here. And I'll say I do feel a little bit maybe underqualified for this, just in that I'm not a statistician, I'm not a philosopher, and this is stuff that's interesting to me, but I'm certainly not a combatant in the statistics wars.
Yeah.
And this has been a good opportunity to kind of brush up on some of these questions. I always have this kind of maybe just innate skepticism to the idea that statistics can actually say something. And maybe we'll get more into that later. Is that
sounds interesting.
Like statistics sometimes just feels kind of like magic, and something like maybe I shouldn't trust this.
Yeah. That's funny. Yeah, and same here. Like, I mean, I use statistics just a little bit in professionally. I'm an engineer, but not a statistician either. But it's interesting. It's an interesting subject, and as I've been just reading up on different things that have piqued my interest, it's something that keeps on coming up of some of the questions about the nature of statistics, what's behind it, what's going on behind the scenes, what are the different ways we should approach it. So I think that's great. Just two guys who are curious about the subject and kind of exploring it. Now, I don't want you to sell yourself short. You also do have a PhD in mathematics, so definitely some familiarity with that.
Just means that I know all of the things that I don't know. So
yeah, there you go. So I probably think I know more than I do. Actually, I'm sure that's the case. But I appreciate you coming and sharing your thoughts with me. So, and hopefully we can generate some more ideas that are helpful for both of us, and clarify some of our thoughts, or at least get stuff churning up to the surface that we can think more about. So anyway, what has got you interested in the subject?
So I think the big thing is like it's such a kind of central part of the modern world. This is not a purely philosophical line of inquiry. Like the understanding what statistics mean in really a deep sense is really relevant to understanding what is going on in science, what is going on with the things that people claim about the world, and that has ramifications for all sorts of different things. And because of that, you see things like the replication crisis in psychology as a thing that has been talked about ad nauseum, but also this stems from, at least in part, the way that people interact with statistics, and that's going to be based on their understanding of what it means and how it works at kind of a philosophical level.
Yeah, I agree. I mean, it definitely comes up in so many things, and I was just thinking as you said that, why would that be? and the thing that comes to mind is basically that there are there's variability in the things that we know, right? That I guess as I was looking at the article, I go to Stanford Encyclopedia of Philosophy for a lot of these type of topics whenever I'm wanting to kind of get the all the big points. But I like something that they said on there where you're basically, when you're looking at statistics, the two main parts are you got data sets and then distributions. And I think that's kind of a good summary of it, but that comes up all over the place, right? If we're talking about political polling, if we're talking about scientific results, if we're talking about healthcare, the results of medical studies, the outcomes or effectiveness of medications. It's just something that comes up all over the place. And, I was thinking about sometimes we don't necessarily think about all the times like, oh, this works or this doesn't. We don't necessarily talk about what the distribution of that is, or how many times out of a certain number a certain medication will be effective, or what was another example I was thinking of? No, I don't remember. But it comes up in basically at any type of any day of the news. You turn it on and watch it. There's going to be something where they either present something that is statistical or should and don't. So it's relevant in that way.
Yeah, and really understanding where did this come from, and how should I interpret this in the sense of what fact about the world does this statistic encode? Does this kind of claim represent? And is it well founded actually?
Mm-hmm. Mm-hmm.
And that that's a very hard question to answer, and I don't know if I've gotten any closer to it in the time I've spent trying to understand the philosophy. But I think I have a little bit better picture of how the questions maybe fit together.
Yeah, well, because I mean, in science especially, we're wanting to know the way the world is, right? And so if it comes to a question of that, I remember what the example I was trying to think of was. So like in a lot of psychology studies, and recently it's been kind of difficult to share a lot of psychology studies because many of them haven't replicated, and so we're a little bit more skeptical. But I remember like 10 years ago, it was all the rage to be sharing these type of ideas. And the one that always comes to mind is like with priming, how they would bring people in and use certain words or have them exposed to certain words, and like time how long it took them to walk to the elevator, and if they were primed with certain geriatric associated words, they'd walk slower or something. But what would be interesting, and I actually haven't looked at that study in detail, the original one, is like, how many times did that happen? Like, what was the percentage of times? Like, when I first heard that, I was thinking that happens all the time. That every time somebody are primed by these words, they're going to walk slower to the elevator. My guess is that probably wasn't the case. It was probably some number that was unusual enough to for the researchers to say, okay, there's some effect here, which is something a little bit different, and it's a little more complicated, right? So, not to hone in on that example necessarily, but say there were some type of effect some of the time, that would still be something about the world, but it's a little bit more complicated, right? Than that. Okay, whenever somebody is primed by certain words, they're going to act in this way, where the reality might be, yeah, this does happen sometimes, but not all the time. And there are other mechanisms below that could affect why or why not it does happen in the times when it does. And that's really what we want to get to, right? Is the complexity of reality.
Mm-hmm.
And I think one of the benefits also of looking at the statistics of it is that it kind of indicates that underlying complexity, rather than just saying it did happen or it didn't happen.
Yeah, and that complexity, and the reason maybe that studies like this haven't replicated is sometimes this is because, right, we're not interpreting the data correctly, and we're not realizing, oh, this really isn't a large effect, or it only happens sometimes. But then also there's the question of what's the kind of external validity of this study. This happened in an experimental setting, perhaps, so the paper claims. But how does that translate into the real world, or into just maybe even other experimental settings that are not identical to the one that the researchers used? And that's often, I think, one of the places where statistics will break down. You can be very careful and make judicious claims about, this is kind of what we did and what we observed, and this is how likely that would have been to happen by chance if this were not a real effect. But the question is, how does that translate into other settings? And that's much harder to control.
Yeah, that's a very interesting point. It brings to mind sort of beyond statistics generally, but also just in the philosophy of science, this kind of strict empiricism of avoiding metaphysical claims, or also even in extreme versions, I believe it was called instrumentalism or something like that, where you're basically, you wouldn't even say, for example, that a solution has a certain pH. You would say, when a pH strip is dipped in this solution, it turns this color, right? You would drastically limit your claims. And I think that that's kind of fallen out of favor, because we can't really live in the world that way, right? We have to come up, we have to take away some type of idea from it, like, okay, what does this imply? What can I do with this? But transitioning from one to the other can be somewhat perilous.
Yeah, especially in these sorts of, I think, experimental psychology, in what people might call the softer sciences. Maybe it's trickier in those sorts of settings.
Where, right, because of their complexity, right? I
exactly.
mean, softer's not meant as a pejorative here. I don't think. Although it could be, but
the things you're probing are squishier.
Exactly. Yeah. There's so much going on, and it's hard to isolate and control variables, it can be difficult to see the underlying mechanism of what's going on. So yeah, I agree. In those fields, especially, it's mind-bogglingly complicated and difficult. And I think with those type of tests also, what are we after? What do we want to know? I think what most people would want to know is, what does that tell us about the brain and our nature? And that can also be that takes a lot of reflection, right? And that might help with the way we think about how to apply statistical methods, right? Like, think, okay, what is it we're trying to demonstrate here? What are we trying to learn? And in what ways could we make sure that we're not going down the wrong track? Which I think is basically the idea of this severe testing that we've both been reading about. If you think you're doing a certain test, and you say, okay, I know when people are reading this paper, regardless of how limited we make our claims, and say, okay, this was the experimental setup, these were the conditions, we're not making any claim beyond here, but people are going to want to think, okay, what is the takeaway from this? And we should consider, are we addressing those questions? Are we answering those questions? And think about ways to make sure that we're not claiming more than we should, right? Or to try to subject our tests to methods that would catch errors if they are there. Right?
Yeah, exactly. This idea of severity. So I think the book that we're talking about, we both read and getting ready to talk about this this topic. It's called Statistical Inferences, Severe Testing, and the subtitle is Getting Beyond the Statistics Wars. And I'm not sure that the book actually does this. Um,
Yeah.
I get the impression that it's more of just another salvo in the statistics wars, but it has a good overview of, I think, some of the main ideas in philosophy of statistics.
Yes.
This is by Deborah Mayo, and her central concept is this idea of severity, and the idea of a severe test being one that has a high capability of discovering a flaw in your hypothesis.
Right.
And she operationalizes this mainly by looking at things like p-values. And so she's working from a frequentist sort of perspective, but doesn't call herself a frequentist because she doesn't care necessarily about the frequency of events so much as the capability of a test to discover errors. And you can measure that or quantify that in some way by using these p-values or probabilities of finding a discrepancy if one exists, or of not finding a discrepancy even though one did exist.
Could you, just for people who may not be familiar with the idea of p-values, explain what that means? Because it's one that's easy to understand incorrectly.
Yeah, this is a fraught topic, and so the idea behind a p-value is you have some statistical or some question, some research question that you want to answer by doing some sort of statistical analysis, and you formalize this in some way by saying I have a null hypothesis. It's the one that I'm looking for discrepancies from. I'm looking to see if the world does not satisfy this. And so this is typically going to be encoding some maybe either unsurprising state of affairs or one that is maybe nominal, that doesn't that doesn't maybe cause, or that doesn't do anything.
So like as an hopefully this is an okay example. So like if you're testing for the effectiveness of a medication, null hypothesis would be basically that it doesn't do anything.
Right. Or specifically that it does nothing or makes the condition worse.
Oh,
typically.
Yeah.
So that's kind of the pessimistic perspective. And so you'll collect some data, and you'll that data will have some relationship with your hypothesis. And the idea with a p-value is now you have some model for the generation of that data. So you'll know kind of what that data should look like if the null hypothesis is true, and what it shouldn't look like if the null hypothesis is true. And so you'll typically produce some sort of a summary statistic that says kind of how extreme is this data, how far from the expectation is it, assuming that the null hypothesis were true. And that so that statistic, and you can figure out what the distribution of that statistic would be if the null hypothesis is true. And so the probability of getting data kind of that is as extreme or more extreme as the data that you actually collected, under the assumption that there's nothing there, is the p-value.
Right.
So a small p-value is supposed to indicate that there's a large discrepancy from the kind of uninteresting state of affairs.
Right. And I guess one of the trip-ups or misrepresentations sometimes, or I guess just confusions, is that people might think this is the likelihood that the effect is not real, right? So so people might hear like it has a p-value of 1%, so, and say, oh, well, that means there's only a 1% chance that it's not real, that it's not a real effect. But that's not correct. The proper way to think of that would be, in 1% of cases where there is no effect, you would see this result. Right? Is that
exactly
a better way of putting it?
Yeah.
Or you would see this average of results.
Yeah. Or even if there were nothing there, we would have a 1% chance of getting this result.
Right. So, and but yeah, like you said, it does tell us it does tell us something, and it's not, I guess, definitive, because it basically has within it the understanding that this isn't a for sure thing, right? There is a possibility that this is a kind of fluke effect, right? That or that it's on the far end of the bell curve of what we would normally expect to see with no effect. But because we do see it, there's some reason to think, some pretty good reason to think, depending on the value, that there is some effect here.
Yeah. So p-values and this sort of significance testing, called null hypothesis significance testing. These were introduced originally by Fisher, and then elaborated by his kind of students / competitors, Neyman and Pearson. And they had a long feud throughout their careers.
Yeah. That was fascinating.
For reasons that are very hard to parse, because they had almost the same ideas and opinions, and they were just kind of fighting.
Right.
But so one of Fisher's things is, so he comes up with this concept of p-values and statistical significance. All these ideas back in the 1920s and 30s was that we still use today, and you hear thrown around. And so he said, as he was describing the kind of rationale behind this sort of test, was that so we should say that an effect is genuine if we know how to design an experiment that will seldom fail to give a significant result. So it's not just that, okay, we've done one experiment and we got a small p-value, therefore there's something there definitely, and nothing else is needed. It's about having a process that can kind of repeatedly demonstrate the truth or the existence of this effect.
So the need for replicability is basically built into that standard from Fisher.
Yeah. And I think that's a really, that's something that people miss. A lot of practitioners will miss a lot of times this is for reasons of kind of time constraints or just incentives there's not a lot of incentive to do the level of rigorous kind of severe testing that would meet that criterion.
Right.
But that's kind of where it should be in terms of really actually doing a frequentist null hypothesis test.
Yeah, and that was an interesting point from Deborah Mayo as well, is that that it's not really that. I mean, p-values have, I guess, a kind of soiled reputation because of the idea of data dredging or p-hacking. Not adhering to the standard that you just mentioned of repeating the tests several times. But her point, one of her points in the book, was that it's not really the p-value that's the problem. It's that you're not using it in a way that's going to catch or that's going to subject the tests to severe testing, right? It can do that, but you shouldn't be using it to shield your results from falsification. You should be using it to attack to attack it, right? She quoted the physicist guy. Richard Feynman. I have his book up here behind me somewhere. Richard Feynman, where he talked about how there's this kind of ethic of trying to disprove your own theories. When I was in high school, my chemistry teacher in 10th grade, he introduced me to this idea, and I really like it. It stuck with me through the years. He was talking about how sometimes what happens is you get a theory and then you fall in love with it and you kind of want to protect it. But that's not what you should do. You should be doing everything you can to prove it wrong. Still treating it fairly, but seeing every way to see if it withstands all the severe testing. He didn't use that term, but trying to disprove your theory, and then as it keeps on satisfying and passing these tests, you can get a little bit more confident. Now, not all philosophers agree with that, but the general idea of that kind of ethic of I'm doing everything I can to disprove my own theory, that's a powerful idea.
Yeah, I like to think of that as maybe giving the universe every opportunity to prove you wrong.
Mm-hmm. Yeah.
And maybe I think one of a good example of kind of the opposite of this is one of these XKCD cartoons about p-values and maybe p-hacking, but the green jelly bean comic.
Yes,
and
that's an excellent one. Yeah, go ahead and tell it.
So there's there's some scientists and someone comes in and says, I heard that jelly beans cause acne, and the scientists are like, okay, fine, we're playing Minecraft, but we'll go study this question. And then they come back and say, jelly beans were not linked with acne, p less than 0.05. But the person then says, but I just heard it was only one color of jelly beans that was linked with acne. And so they're like, okay, fine, we'll go run some more tests on individual colors of jelly beans. And so they run it on green and blue and orange and mauve and magenta and 20 different colors. And well, it just happens that one of them turns out to be associated with acne. I think it's the green jelly bean.
Yeah.
At a level of significance of 0.05. And the point is that if you ran 20 of these tests independently, even if there were no effect, what we should expect, we shouldn't be surprised to see that one of them came out positive. That's right. The interpretation of the p-value, that, well, there's a 1 in 20 chance of getting this result even if there is no effect.
Exactly, yeah. Yeah, I like that cartoon. It's an excellent illustration of the idea, right? That it's basically built into the whole program of the practice, that you're going to get some false positive after a certain number of replications. So yeah, I think that's a good illustration of it.
But so I looked at there's a statistics kind of Stack Exchange site, and there's a discussion of that cartoon and several other XKCD statistics cartoons there. And there's some kind of surprisingly subtle discussion of, okay, where did the researchers go wrong? And there's the obvious answer that so they didn't correct for multiple comparisons. So they ran multiple tests. But their main central question was, do jelly beans cause acne? And if you run 20 different tests and say, well, we'll say that jelly beans cause acne if one of them comes out positive, you really need to correct for the number of tests that you're running. But there's some subtle questions. So if you beforehand, before this person came and asked you about jelly beans, if you really had a theory that green jelly beans and green jelly beans specifically should cause acne, and you ran that test, and then the other people in your lab ran the other 19 tests, now should you correct? What's the right thing to do there? There's some subtle issues, and one way to think about this and evaluate it is maybe with this severity criterion. But that's going to rely on kind of characterizing what is the procedure I'm following to test this. And that's sometimes a little bit fuzzy.
Yeah, I'll have to go read that Stack Exchange. That sounds interesting. Yeah, because when I saw the cartoon, my thought was, well, then you need to run a test again on green jelly beans and see if you still get that same effect over and over again. I mean, it seems like that should, assuming there's no correlation.
It should.
Yeah,
and really, that's probably the right thing to do.
I'm still avoiding green jelly beans, but
But I mean running these sorts of experiments can be expensive, right? You have to find independent data sources about consumption of jelly beans and acne. But so there are situations where this sort of multiple comparison problem is more obvious, and these sorts of corrections are more important than maybe these kind of sequential data dredging studies.
Yeah.
So
An interesting thought there I was just had. I mean, so we're talking about, subjecting it to more testing and that, which is kind of a frequentist approach. But I was wondering if a Bayesian filter might help with that as well. Like, if your prior is that jelly beans don't cause acne, or green jelly beans don't cause acne, and then you see that there's one effect, should that be a red flag in some way? Whereas if you're just mindlessly running the test without any type of prior probability or worrying about mechanisms, not that frequentists do that, right? I mean, I think that's one of our ideas, is that it's not so rigidly automatized. but anyway, the general logic or philosophy of a Bayesian approach would be, well, wait, that doesn't make any sense, and that would maybe key you into doing a little bit more looking at that.
Yeah, and I think that would help, especially if you see a news article about a study that discovers that green jelly beans cause acne, and when you're deciding what to believe for yourself, it's kind of a reasonable thing to do, at least to take some prior probability that you had. Maybe you formally had that, maybe you didn't, but think, how does this information change what I already believed? And this is where knowing maybe how that green jelly beans cause acne result was produced is important.
Right. Well, oh, sorry. So go ahead.
Oh, so your prior would still kind of modulate the effect of that. It would kind of attenuate. All right, you're not going to swing all the way to believing definitely green jelly beans cause acne, but it still might kind of push you a little bit in that direction.
Right, your posterior would change a little bit, based on that information. Yeah. I was thinking about another cartoon that you had shared, an XKCD one, about the box that sees if the sun has exploded or something, and then it rolls die, and if the sun has exploded, then it will always roll double sixes or something, right? I think.
Yeah. So it says yes if either the sun exploded or it rolled two sixes.
Okay. Yeah. So then the machine rolls two sixes, and the frequentist says, well, there's only a certain percentage of that percent chance of that happening, and it's below our p-value of 5%, and so I'm going to assume the sun has exploded. And the Bayesian said, I'll bet you $50 it hasn't. And the joke there being that the Bayesian is prior of the sun exploding is so low. If you were to plug in those values of certain event of a certain event happening, your hypothesis, the probability of the event based on the hypothesis, if you plug that all into the equation, the probability that the sun has exploded based on that result is still very, very low. So and it unfair to the frequentists, of course, but it's funny.
Yeah, and this is one of those situations where I think a reasonable Bayesian and a reasonable frequentist would not come to different conclusions. Right. They would agree the sun has probably not exploded, and the frequentist would just say that given what we know about the experimental setup here, there's this test is not appropriate. This kind of just pick the threshold of 0.05 and yes if below and no if above, yeah. So that's a good illustration of things that can come up when you're designing experiments or trying to interpret experiments. You can be aware that there might be subtle behavior like this that looks like this. It's sort of, all right, my apparatus lies to me with a certain probability, and I need to keep that in mind as I analyze the data that came from it.
Right. Yeah. Well, and with Deborah Mayo, one of her points, I think it impinges on a lot of stuff in the philosophy of science about method, right? So
Mhm.
Deborah Mayo, her point is kind of like, well, we can't just uh, toss out methods, right? We still have to have certain types of methods or rules that we use. Um, but I think she's also recognizing that they have to be used in a human way, kind of in a reflective way, and it can't be completely algorithmic or robotic,
Mhm.
where there's not a thinking person behind it. It reminds me of uh, Paul Feyerabend, philosopher of science. He wrote a book called Against Method, and he was like on the total opposite of that, where he was like, scientists, I mean, they have methods, but that's not really how science works. It's just kind of by hunches and practices, and if they're convinced or not, and there's not really a way to systematize it, even if we pretend that that's what we're doing. I think most people think that's too extreme. It's an interesting idea, but Mayo seems to be kind of in between there, right? To just at least allowing some leeway to get above the methods a little bit and reflect on them.
Yeah. And yeah, this question of methods, I think, is a kind of central one to statistics and really understanding what makes it work. I think one of the examples that really struck me from Mayo's book um, was when she's arguing against, and I'm not sure how many Bayesians actually believe this, but there are some who believe that they treat the data as basically just given to you, handed to you, and there's not really an analysis of the method by which you acquired the data. So in particular, these Bayesians at least would not distinguish between, let's say, I roll dice and I decide to roll 20 times, and I look at the average that I got from that, and they wouldn't distinguish between that and a situation where I decide I'm going to roll dice until I get an average total roll of 5.
Hmm.
And it just happened that I rolled 20 times.
Hmm.
And the Bayesians, and it's hard to formalize in a Bayesian framework how those would differ.
Hmm.
But from a frequentist framework where you're looking at kind of the generating method for the data, those are very different things.
Right.
There's no way you could ever get an average below 5 if you don't stop until you get above 5.
Right. Right.
And so you shouldn't be surprised at all to get an average above 5. Whereas
Right.
in this kind of Bayesian setting, where you're not taking into account this kind of optional stopping, then you can't necessarily tell the difference.
For
And
my
some,
benefit, not being able to do the mental math in my head, is that what the average would be in the infinite? That it would be 5?
No, the average would be 3.5. I want to say.
Oh, okay.
Right.
I was gonna say 5 seems high, but
Right.
okay.
So
But that was your point.
the point is you're trying to, and there's, this is probably a bad example because there's not a guarantee that you'll actually get above 5. I believe I don't think that you can guarantee that. So you might just end up rolling dice forever.
Right. Okay. But your point being,
but
that
there are situations
it
where
could happen.
Right.
Yeah, you could get those data sets, and I guess from one possible Bayesian perspective, there wouldn't be a distinguishment between those.
Exactly. And right. And so, and there are Bayesians who would argue that, yeah, there's absolutely nothing wrong with that. The data is the data. The data is given, and you just need to condition on the data and apply Bayes' rule and get your posterior probabilities. I don't think that would be a common position among actual Bayesian statisticians, but Mayo at least found a few that would argue this.
Yeah. Yeah, I guess, I wouldn't expect it to be that common, but so I don't want to straw man necessarily, but yeah, you're probably right that there are some, at least who would go along with that. Yeah. So the how
Right, but
would
the
you? Yeah, so the question is, when you have these different methods, um, how do you? What's the method of the method, right? Like, how do you? Because we've talked about how certain methods could be more applicable in certain situations. Like, um, I think we're both kind of like um, not really wanting to take sides in statistical sports, right? We're probably far enough removed from it that
yeah.
it wouldn't even make sense. So there'll be no need for me to go into the witness protection program after this. But we were kind of talking about like, well, okay, one method might work well in this type of situation, or it might work well in this type of situation. But that's kind of like not too systematic. Although I guess you did give some criteria, which might apply as a method of a method.
Yeah, and that's a tricky question, and you don't find a lot of people telling you which, because they all want to advocate for their
Right.
pet
Which seems like a
approach.
problem. But
There are definitely a lot of kind of eclecticists
mhm,
in the statistical community, um, and um, and they'll point out the different kinds of guarantees maybe that you'll get from a frequentist test or confidence interval versus a Bayesian confidence interval or a
mhm,
credible interval. Um, and so you might think about, okay, what do I already know? So do I have a prior really? Do I have kind of reasonable information that I can encode in a probability distribution um, beforehand?
right.
And and then on the other hand, is the output, do I care if the output depends on a prior? Am I trying to convince someone else who might not have the same prior as me? Uh, and in situations like that, well, you might want to either kind of use a Bayesian method that doesn't depend very strongly on the prior, which there are some, but it kind of feels like, well, that's not how you're supposed to use it.
Mhm.
But people do this. Or you should do something that's more frequentist, where you can give different guarantees, but you can use this to argue in kind of an interpersonally neutral way, that it doesn't depend on your subjective prior probabilities.
Yeah. Well, so as far as like the prior probabilities, whether it um, matters or not, I mean, there would seem to be some cases where, I mean, it almost objectively does. Like, so the main one I think about is this example of the uh, test for a certain disease, right?
Mhm.
Um, like that's one where I see like, oh, Bayes' theorem works really well there because, and I'm trying to pull it
Yeah,
up.
this
Uh,
diagnostic testing in general. Yeah,
yeah.
where you,
Well, let me. I'll read like an example of a problem. Let's see. Do I have that one? I posted it just a little bit ago. Hold on a second. And then I was gonna want to look for what the answer is because this is one of those things like I know it's more complicated than it sounds, but then I can never remember actually how to do it. um, okay, so here's an example where like Bayes' theorem, you could just plug in the numbers for this one and get an answer. Um, okay, so this is suppose a certain disease has an incidence rate of 0.1%. Um, a test has been devised to detect this disease and it has a false positive rate of 5%. A randomly selected person takes the test and tests positive. What is the probability that this person actually has the disease? And this is kind of like a classic example where, it's used to show like how statistics is hard or humans aren't as, I guess, numerate or rational as we might think. But it's definitely not obvious to me either. But so like, they'll even have people in medical school give them this test and the answers vary, right? You think like, to somebody who hasn't been exposed to this type of thing before, you think like, oh, false positive rate of 5%. So 95% chance the person has the disease, which is not correct. Or it could go lower. But I mean, it's actually, I was trying to look it up. I think it's less than 2% or something like that. Um, and the reason for that just because there's such a low prior for the disease in the first place. Most people who are going to get this test don't have it, and then the 5% that still applies to the 5% who get the false positive, or sorry, the false positive is going to cause that most of the people who get a positive don't have it by the vast majority, and that's because of the prior. But the reason I bring that up being that seems like a case where, I mean, you'd kind of have to use the Bayesian approach, right? I mean, it's like, I tell me if I'm wrong there, but like the prior almost seems objectively mandated by the nature of the situation.
Yeah, and I think that's a really good situation in which to use Bayes' theorem and these kinds of reasonings with priors.
And that's an easy case, right? I mean, that's kind of the...
Yeah, it's maybe like the canonical case.
The paradigm, yeah, exactly. Yeah.
And this is why you don't give everyone an HIV test or test for whatever disease, because that's not going to give you a lot of information.
Right. Yeah, I was thinking about this as like, because we don't only go by the test, right? Somebody already has some reason to think that they have it, which I guess is another thing of priors, right? They have symptoms, or they've been exposed in some way. Yeah.
And that's the point at which you start to go from, so there's you could take a purely frequentist interpretation about kind of applying Bayes' rule in this sense. Your prior probability is in fact just a frequency in the population of something happening.
Yeah, there's nothing about subjective belief. And to back up a little bit, for those who may not know of the difference, so there's Bayes' theorem, right? And then there's Bayesianism, which is kind of how do we interpret what these probabilities are, and the Bayesian position would be these are basically degrees of belief in a certain probability.
Yeah, exactly. And so there's not really necessarily a subjective degree of belief to what proportion of the population has this disease.
Right.
So you can reason about this and just interpret all of your probabilities as frequencies. And because this is a theorem of probability, it holds no matter how you're interpreting probability.
Right. But I see your point. Like if somebody, like say we're talking about COVID, if somebody starts coughing or has been around other people who have had COVID, or they don't wear masks, that gets seems a lot more subjective, I guess.
And you could try and quantify this. Okay, what proportion of people who have a cough now have COVID, or what proportion of people who have, I don't know, some other symptom, or from what proportion of people from this population. And now you still have this kind of frequentist interpretation, but as you narrow down sufficiently, it starts to feel less and less like probability and more just like, all right, I've narrowed down, subgroup by subgroup to, oh, you're the only person left. Now what's this test telling me?
That's funny. Yeah, I see that's an interesting illustration. Yeah, of the transition from the kind of frequentist to subjective understanding of it. I like that. I hadn't considered that before. Yeah, that's very good. So yeah, I mean, those were, you had mentioned like when we're talking about updating beliefs, a Bayesian subjectivist interpretation makes a lot of sense. And then what was the one where you were saying where a frequentist model might make more sense? Like you were talking about particle physics, or in a lot of scientific results.
Yeah, so in a lot of scientific settings, you're not really trying to produce kind of a probability distribution on kind of models of the world. It's something that's kind of that's ill-defined, and scientists typically are going to want to be able to justify their results to people that don't necessarily share the same priors as them, or that or without reference maybe to whatever prior beliefs. So you're trying to give evidence for something, and evidence that you have stringently tested it, that it has undergone some severe test. And frequentist statistics are often well suited for this, because you can, so for one thing, the null hypothesis test is really, if you set it up properly, the existence of a discrepancy is at the very least going to be interesting to someone. And you can argue about what that indicates about the world, but you can collect that. Whereas if I come out at the end of some Bayesian analysis and say, all right, I now assign probability 99% to this hypothesis, that may or may not be interesting depending on what your prior probabilities were.
I wonder if you could just like say Bayesianism won the statistics wars and we were all Bayesians. Would you like say like, well, plug in your prior and here, but even then, I mean, because you still have to. It's not only priors, right? There are because there's like your dependent, the way that you assign a probability of a certain result based on the hypothesis. So there are quite a few values.
And that, and then that depends on maybe how all-encompassing your Bayesian model is. There's levels at which those conditional probabilities are not going to be really controversial because they're just kind of defined by the mathematics.
Right.
But then at other situations, you'll see maybe people online. I've seen a number of experiments where people are trying to construct models to figure out the probabilities of certain things that we don't know the answer to, like what happened to Malaysian Airlines flight, 397?
Yeah.
And
no, wait, was that the one that went down over Malaysia or over Ukraine?
Malaysia.
Oh, okay, yeah, I remember that. Yeah,
the other one I think we know got shot down by.
Oh, that's right. Yeah, right.
So yeah, this one, and so they'll come up with a list of hypotheses and then maybe kind of list out all of the evidence that they know, and then they'll try and figure out what should the conditional probability of this hypothesis given this evidence be. Yeah. And you're plugging in a bunch of numbers, and it's not clear where those numbers come from. You can try and get some kind of look for similar situations, look for base rates, and that's helpful.
Yeah.
But this is a really tricky problem when you've got something that's not well defined. You don't have these really well defined conditional probabilities. And so I looked at this and it just kind of like, oh, that's cool that they did that. And
it seems kind of like the Drake equation in a way, like
exactly
where you don't necessarily have the numbers to do it. Like it's not necessarily that there's anything wrong with the method, but it's just having
there's a lot of parameters.
Yeah.
Who was it? There's a mathematician who said that, give me 4 parameters and I can make an elephant, and with 5 I can make it wiggle its nose.
Very nice. Yeah. I mean, in a way, it is certainly, it can induce rigorous thinking. To be able to think in that way, and I guess that's also one of the lifestyle or worldview approaches, right? Is that you have a coherent mixture of beliefs, right? And that's one of the things about Bayesianism as well, is that you're supposed to have it as if you were to bet on all your beliefs, you would not be losing money, right? That everything coheres, everything, all the probabilities that are mutually exclusive add up to 1, or at least they don't add up to more than 1. There's this idea of the Dutch book argument where if you were to bet 80% on all the horses at the horse race, obviously you're going to lose money because only one of them is going to win. I don't know. I've never bet on horse races, so I don't know if I said that right. But so that you can't add up your probability to more than 1, or else. And not that it has to do with actually betting, but it's the principle of the matter, right? That all of your ideas make sense. And there's appeal to that, right? I mean, certainly an ideal that I guess I'd want to work toward.
It's the difficulty comes when you realize how many things there are to have ideas about,
right?
And you run into this essentially this curse of dimensionality, in that you now have to, every time you add a new event, you've doubled the number of things that you have to kind of have opinions about, because now you have the conjunction of that event with every other event that you have an opinion about, and the conjunction of like that event not happening with everything else. So you've doubled the size of your number of probabilities. And once you have more than a handful of things, like you start running out of space to store that in a computer even.
Right. Exactly. The actual physical computation of that would be intractable, and then for a human mind to be able to do that would certainly not be possible. That's why I think it would have to be just an in principle type of ideal, rather than something that's actually
and there are ways to kind of get around that, but that means that you can't represent every possible distribution of probabilities. You kind of narrowed your focus to ones that are plausible, that kind of factor in nice ways.
I mean, it's certainly, you could, it almost seems like you could identify better irrational activities. Like, I'm trying to think of an example, but like if you take out, if you think that your house is going to burn down, and you decide not to you decide to go and spend all your money on expensive cars rather than an insurance policy or something, when you have a really high probability, just something like that, where you think that it's just not a rational way to respond. Like the way that you should respond given that probability just doesn't make sense. And I'm sure I could have thought of a better example, but you got the idea.
And as you said, these exercises I think are valuable, but there's a fine line maybe between using them to kind of refine your understanding of the world, or kind of make your opinions or judgments about the world more rational, and just using them to justify things that you've already done. And maybe this is another kind of instantiation of the question of severe testing. Right? Have I given kind of this method of assigning probabilities and conditional probabilities, have I given it a chance to prove me wrong?
Right. Yeah. And I do think that, I mean, I agree that Mayo doesn't really get beyond the statistics wars, but there is a little bit of an aspect of kind of at least stepping back from the current rivals and seeing, okay, what is it that we're trying to do here, right? And severe testing could be one example. I mean, I'm pretty convinced that that's a good idea. Is there disagreement or challenging of that? And I'll say, she does say severe testing isn't the only thing we should do, right? I mean, we want actually interesting, non-trivial things that we learn. But has she been challenged on severe testing, like that it's not something we should be pursuing?
That's a good question. I think I don't think I've seen anyone kind of argue that shouldn't be a goal. They might say, they might not adopt that terminology, but they might kind of refer to her and say severe, that's, and maybe kind of say, oh, here's how you could interpret what I'm doing in that framework. So I don't know. Again, there's probably someone but I can't imagine that there would be a lot of people who would seriously disagree that should be a goal of statistics, at least.
Yeah. Now, one, I guess kind of in the opposite direction of that I was thinking of is of like taking severity maybe too far. So when I was getting into Mayo, I was thinking, oh, she seems pretty Popperian. Philosopher of science, Karl Popper. But not quite. And I think she mentioned this.
She has a section where she talks about where they differ.
So, and this kind of gets into the question of evidence and induction that I think we listed that we wanted to talk about a little bit. But for Popper, you never really demonstrate something as true. You never really conclude that some theory is correct. All you can do is disprove. That's the only thing you can do. That seems like that's about as severe as you can get, right? I don't think you can get more severe than that. And I haven't seen many people pick that up. Like Popper's kind of a hero in popular scientific thought of like falsifiability, right? And which is a great concept. I definitely like the idea of falsifiability. I don't think people realize the extent to which he advocated that is like, that's all there is.
Yeah.
Like for Popper, evolution isn't true, right? It just hasn't been falsified yet, or pick your theory. And he's content with that, and I guess you could view the world in that way. Most people don't want to do that. So Mayo still wants to be able to say, okay, we are able to get at reality and say something about it. Not conclusively, but we can at least provisionally, with some degree of confidence, say this is the way the world is, after submitting things to severe testing and that it's withstood all these things. So
yeah, she has a really I liked her concept. I think she called it liftoff, of the idea that that a conclusion, a premise, some theory can be more robustly tested maybe than any of the individual pieces of evidence that contribute to it, right? That you kind of assemble these pieces of evidence, and if you assemble them in the right way, you get liftoff. You kind of get beyond the narrow kind of things that they say individually and their individual flaws, and you can kind of play those off of each other. It reminded me of so one of the things that I've been reading about a little bit lately is this is kind of, okay, how do we produce things that are very mechanically precise, right? How do you make something that is very, very flat?
Yeah.
And if you think about this for a minute, it's kind of weird that we can make things that are flat starting with things that are not flat. And I think this is
how do you get the first flat thing to make
right.
Exactly, yeah.
And this is I think an example of that kind of liftoff. There's a book called The Foundations of Mechanical Accuracy that kind of goes into this. It's one of these. It was published by some machine company.
That sounds fascinating. 70s. Yeah.
And
because I'm an engineer, so this is
right.
This sounds very interesting to me.
It's more technical than I expected it to be, but they talk about the things that they do to produce very flat surfaces and very straight, like straight edges. And one of the key principles is this idea of self-truing, of self-correction. So you want to build something in a shape where you can easily detect flaws in it. So if you're building a straight edge, well, you want to be able to know whether it's bowed or twisted. So they construct these straight edges, and they put them maybe in a groove, and you're trying to test whether maybe the corner of this straight edge, it's basically just a big long extruded square. And you lay it in the groove, and you look at how it sits in the groove there, and then you turn it around. And there's certain things that are asymmetric. If it's asymmetric in that certain way, you'll be able to detect that. And the same thing with very flat surfaces. So you start by just kind of making two surfaces that are flat, and you slide them across each other, and that's going to make them mostly flat. But there's actually there are things that can happen. You might have them kind of bowed in complementary ways. And so now you have to be able to rotate them maybe 90 degrees and check that they're flat still in that they still conform to each other in that setting.
Yeah. So are you thinking of kind of an analogy here to
right
submitting kind of finding all these different ways that you can test ideas?
Exactly.
In a similar way that you would have to make a surface flat from multiple angles and multiple directions.
Yeah, and you can choose maybe your tests or your experiments in ways that would make it easy to reveal those flaws. And I think that's maybe a key principle behind the idea of severity is we have the chance to not just take the data as given, but actually influence the way that we obtain it. And if we do that right, then we can get a much better picture of where things are broken and where they aren't.
Yeah. Something I was thinking about with this, and I keep coming back to this kind of um, inability to make everything a complete automatic algorithmic process.
Mhm.
Now, I don't know if that's a fundamental inability. Like, I'm on AI, for instance. I have this view that maybe it is possible to create a self-conscious machine, but it's just really hard, and we don't know how to do it, right? So for practical purposes, right now, it's not possible. And it kind of seems similar to these type of things, where if you're deciding what test to submit it to, I think maybe in principle there is a way to come up with some type of algorithm where you could have submit it to a program and say, okay, here's the data I'm looking at. Here's my scientific question. Tell me how to test this hypothesis and give every opportunity for the universe to disprove it. And then the computer tells you exactly what to do. Maybe that's possible in principle. I don't think we're there yet. It still seems like there's a lot of the, for lack of a better word, the human intuition that is only available to us self-conscious beings for the moment. That we kind of have to look at this and be like, what makes sense? What kind of problem is this? What will be convincing to everyone? Where if I were looking at this and I'm in a conference and somebody's presenting this data, when I stand up to give my question/comment, what is it going to be, right? And then do that, address it, find some way to be ready and have that in your pocket to say, oh yeah, we accounted for that. And it seems like that that sort of at the moment not fully algorithmic process is necessary.
Yeah, and yeah, this it's probably I think people sometimes call this an AI complete problem, right? The question of what's the right way to test this hypothesis statistically. If you can come up with an algorithm that solves that, you've basically solved the hard problem of artificial intelligence.
I like that.
So it's AI complete. AI complete in the same way that a problem might be NP complete. So it's equivalent to this other class of problems that we know are hard. They're not as hard as AI, at least in some sense.
I'm gonna have to use that, an AI complete problem. So yeah, basically that if you were able to do this, to have a machine do that, you'd basically have invented AI in order to. Yeah. Okay, I like that. That's a good little mental module I'll have to store away there. I like it. Cool. Did you want to get into well, okay, I want to get to like evidence and the problem of induction and all that. But since we've talked about Bayesianism, I wanted to touch on one point. Because like we were talking with Jared, who's been on the podcast a number of times as well, and he brought up how Bayesian methods are used in a lot of fields, and that's correct. And this is something I don't know if you have much knowledge of it or comments on it. My general impression is that a lot of Bayesian methods, like in machine learning, for instance, seem to be kind of a different ball game than Bayesianism in like statistics, if you're trying to make some claim about the nature of reality or the world, or some event that happened in history. So like with machine learning, for instance, if you're doing like prediction of text or something, or just prediction of any event that's going to happen, you have priors and you have functions that are going to be updated. You have loss functions that it will respond to. I mean, it's a very it is certainly Bayesian in its structure, right? Because you have these values that you start with that get updated progressively as the programs run, right? So in its logic, it certainly is Bayesian. I don't know, like, is that the same thing as Bayesianism?
Yeah, I'm not sure. I think maybe part of what you're picking up on is the difference, and of course there are some people who claim that there really isn't a difference, but the difference between machine learning and statistics, in that machine learning is much more interested in kind of making concrete predictions in individual situations, whereas statistics is often more about global inferences from smaller amounts of data.
Okay.
So in machine learning, you're trying to build a system that will do something in the
Right.
world. It will, it will look at a picture and tell you what that's a picture of. It will, it will generate some text in the style of some author. Whereas in statistics, you have a question and you're trying to answer it, and you're using, typically you'll have less kind of input data and you'll have more structure to that data, or things like that. And so the senses in which I think machine learning is Bayesian, I think one of the things that machine learning has done is shown that subjective probabilities are at the very least a very useful thing. So for instance, with language models, the idea that you could maybe assign a probability to a sentence was, for a long time, there are a lot of people who said that doesn't make any sense at all. And then we get these models like GPT-2 and 3 and BERT, and that do exactly that, assign probabilities to sentences. And they do a phenomenal job, much better than anything else that we've seen at kind of generating text by using this sort of probabilistic subjective model. And it's only sort of subjective because it's also based on huge corpuses of text and looking at actual statistical frequencies within it.
Exactly. Yeah, you have your training data in machine learning.
But what it does is it spits out now the probability of of a distribution for the next word in a sentence.
Right.
And that's how these things work. So there's this I don't know, it feels kind of engineering-y, like that there's not, they're doing things because they work maybe, and not because there's a philosophy behind it. And they find, assigning probabilities to words works. So
exactly.
we'll
I mean, it seemed
whatever it
I'm
means.
no expert in machine learning, but when I look at it, it's like, oh, well, yeah, of course you would do it that way. That makes lots of sense.
Yeah.
And another thing, I don't remember. I think this might have been before we knew you, but we had read this book by Andy Clark, philosopher of mind, and he has this book called Surfing Uncertainty, and he gets into prediction processing model of the mind, which is interesting, and so it has Bayesian elements as well, and that's an interesting idea that, and if you think about it, just basically that our neurons seem to be conditioned by certain chemical environments, and then they will respond to dramatic changes in those environments in more dramatic ways than if there's a static constant environment. So basically, that there's kind of there's sort of a Bayesian logic at the neuronal level too, or seems to be, and then also maybe at the level, brain anatomical level. So there's some interesting ideas there. But again, it seems something a little bit different. It's more like that's the machinery.
Or a way to interpret the machinery, right?
Yes, probably in that case, yeah. Because you're not building a brain, you're looking at the brain and thinking of a way that makes sense to model it. Yeah. So anyway, I just wanted to mention those because I didn't want to. I wanted to give Bayesian principles their due, and they certainly have very advanced technical applications out there in the world, with people who are inventing stuff and making the world run. So it's definitely,
definitely.
So don't want to shortchange that at all. Anyway, do you want to get a little bit into induction?
Sure. And I'm not entirely sure what to say about induction. it's a very hard problem.
It is, yeah, but it related to statistics and probability, I think.
Yeah, definitely.
And yeah, and I guess
Yeah, this
I'll
is like,
address. You said it's a very hard problem. People have been working on this for centuries, and it doesn't seem to have. Depending on what type of solution you want, it doesn't seem to have one, unless you're able to accept a more modest type of solution.
yeah, and I am not probably as familiar with the different solutions or even with all of the issues, but my sense, and this is again kind of my general statistical skepticism coming out, is that it's so hard that I'm just not going to think about it a lot of the time. Like I can kind of intuitively see situations where, all right, I'm okay with this being inductively justified, but I don't know how to formalize any of that.
Right. Well, and so I guess probably the classical problem of induction is basically trying to justify induction by deduction, right? So the problem is with deduction, you're able to go from premises to conclusions, and in every case that a premise is true, a conclusion must be true. It follows necessarily if you're going to accept logic at all, right? If P, then Q, P, therefore Q, right? That's a modus ponens logical principle. If P happens, Q must happen. That follows deductively. Now, induction is basically you're taking a small set, and this is where statistic comes in, and you're generalizing, right? So, and the question is, how can you justify that? You've only looked at a small sample of data, and you're making conclusions about the whole thing. So, like polling, for example, like you poll a certain number of people about who they're going to vote for president, and then you say, this is how all of America, or all likely voters, are planning to vote right now. And you think, how did you make that jump? But it seems to work, right? But there's not really a way to say deductively why it works. And the circularity of it is kind of funny, is that the only way we can really justify it is inductively. It's like, well, we've been doing it and it seems to work, which is an inductive. Another thing of induction is, so you could go from small to large, and then you could also go from present to future, right? Or the next element in the series. So like the sun coming up every morning, right? Comes up every morning. You think it's going to keep on happening. And David Hume, like, his big point was like, of course we think that. It makes sense to think that, or maybe it doesn't make sense deductively, but you'd be crazy not to think that. But there's no way you can really say for sure that it will. And another example I like is, chickens in the coop. They say every day the farmer has brought us food, and so every day he will in the future, until the day he brings the axe, right?
Exactly. Yeah, so, and I'm not sure, that there is a full answer to that. I think the narrower you try to make your inductive questions, the better you can probably try and answer or justify induction. So, polling people to figure out who they're going to vote for is a much easier inductive question than kind of, well, maybe it's a different inductive question than will the sun rise tomorrow?
Right. Yeah, it's a different type. Yep.
And maybe part of this has to do with the consequences when your induction is wrong in either situation.
Right. Yeah. Well, and the thing is, in science, the uncomfortable thing is, so one of the logical fallacies of deductive logic is affirming the consequent. So, if P then Q, P therefore Q, that's modus ponens, so that's legitimate. That does follow. What is not deductively conclusive is the following. So if P then Q, Q therefore P. You can't do that. It may be true, and it often is true, but it can't be true because there could be some other way to get to Q. And the uncomfortable thing in science is that we often do that, right? So we'll say like, if this hypothesis, if my theory of reality is true, then we should observe this result. And then we go out and we find that result is in fact there. And so we say, oh, well, my theory must be true. And that's convincing, right? It's convincing, but there could be other reasons that this event happened, right? And we all, well, maybe we don't all know it. We don't always think about it, but at least philosophers of science know it. And if you present it to scientists, they'll be like, well, okay, yeah, I suppose that's true, but I'm just going to keep doing what I'm doing.
Yeah. I think there's a line in Mayo's book where she calls a certain type of Bayesian inference statistical or probabilistic affirming the consequence.
Oh, nice.
And there's a sense in which that's true, right? A conditional probability, if probability of P given Q is high, that's sort of like if Q, then probably P, or
yeah,
switch them around, whatever.
Right.
And so now applying Bayes' rule, now you're saying is like P, therefore probably Q, modulo applying your priors. And that's valid. That's a valid because of the laws of probability. And so you're assuming that the laws of probability apply here. And null hypothesis testing, if you try and take the outputs very, very narrowly of what it says, doesn't quite fail to do that. So you have you have something of the form like, if the null hypothesis is true, then probably my p-value is greater than 0.05. In fact, with probability 95%.
Right.
And so now if you now what you're doing is, when you reject the null hypothesis, I think, and I'm doing this on the fly, so maybe I'm doing this wrong, but I think what you're doing is now you're applying the contrapositive. Now you're saying, so if P, then probably Q, not Q, therefore probably not P, which is not quite the same. And in fact, the contrapositive is deductively valid. But probably is a really, really weird kind of logical operator.
Yeah.
And it doesn't behave like you would expect it to. So I'm not sure that that's valid at all in any way.
Yeah. And I'll just point out, like, trying to keep track of all this stuff it gets very confusing, and it's totally understandable, like why statistics is a difficult issue, in the public, in any type of discipline. I mean, this is pretty pretty heavy stuff. I think with the problem of induction, it's one of those things where I don't see a solution other than ways to deal with it, right? And it's probably one of those things where we're gonna settle for it, right? We'll settle for that. So, for example, you could go Popper style and say, like, well, yeah, you can never prove a theory based on any piece of evidence, and that's all there is to it. And technically, yes, at least with absolute certainty, right? With deductive certainty. But I don't think we want to do that, right? We want to be able to think, okay, this theory is correct. This is the way the world is. Maybe with in the back of our mind, just thinking how, okay, all models are wrong in a sense, and Mayo harps on that a little bit. It's like, okay, yeah, all models are wrong, but come on, let's not just leave it there, right? We still need to use them, and I think anyone who's at least a little bit philosophical about science realizes, okay, yeah, we don't know for certain these things, and they're going to be revised in the future, and we're just kind of cool with that.
But yeah, you have to do something now, and
right. Yeah. Well, and so related to that was another issue you had brought up was what counts as evidence,
mm-hmm.
right? And that's definitely related also, because it's
right.
basically a type of inductive reasoning.
Yeah, and how do you measure how good evidence is? And so you have maybe the Bayesian interpretation, which is something to do with Bayes factors, like how much bigger does it make your posterior probability after observing this data? Or you can try and use p-values of something to measure how good evidence is. But in both of those situations, you're doing this kind of, you're observing the consequence of some model, and
right.
not, so you're observing outputs and trying to infer inputs from that. There's induction going on here.
And this is fun. So like there are so many models for the way that we could understand evidence, and the ways that and a lot of them are plausible and probably make sense and maybe are good ways to think about them. But what gets fun is the examples of where they seem to break down. So are you familiar with Nelson Goodman's new riddle of induction?
No.
I mean that one's crazy, and I can't even say I necessarily understand it. But where was I? Oh, I was reading a different book. It was by Theory and Reality, and by who is this? He's an excellent author of science. I'll just pull it up because I like to recommend. But he was talking about this, and also in terms of Bayesianism. Peter Godfrey Smith. That's right. He has a book called Theory and Reality that gets into these philosophy of science types of things. But Nelson Goodman, he has this this riddle where he talks about how you could define certain properties in totally ridiculous ways, but the logic of them works out in ways that it's kind of hard to object to. So he talks about these properties called GRU and Bleen. So like an object is green. Let's see, where does he put it? If it was observed as green, before time t. Okay, an object is GRU if and only if it is observed before t and is green, or else not so observed and is blue. An object is Bleen if and only if it is observed before t and is blue, or else is not observed and is green. And I won't even get into like explaining like why he uses this, but it gets so confusing, and there are just these crazy examples that he uses. And I think he's responding to Rudolf Carnap in one of his theories of evidence. And I apologize for not being prepared to like explain this, but I just wanted to mention that because it's like you get into stuff like that where people come up with just the craziest counterexamples for any theory of evidence and induction. There's another one about the Ravens paradox. So like, I think that one was also Carnap. Have you heard of that one?
I've heard the term. I don't remember what it is.
I'll
heard
try
the
to
GRU and
explain
Bleen
it.
one. I didn't know that it was. I've heard
that one.
That one. But
yeah,
I didn't know
that
was
nuts. So the Ravens paradox is like you have this hypothesis: all ravens are black, and then so then you say, okay, well, if you see a raven and it's black, does that count as confirmation of the hypothesis? Obviously, a raven that's not black would disprove it. But then also logically, anything that is not black and not a raven would also contribute as evidence to the hypothesis. Anything that is black and not a raven wouldn't. But there's this joke that you could do indoor ornithology by just being in a room and looking at a bunch of things that are not black and not ravens, and that would contribute to your hypothesis. And one of the responses to that was like, well, okay, yeah, that does technically, by this model of evidence, contribute, but it's just a very small degree of evidence. The GRU and the Bleen example, Peter Godfrey Smith had also talked about how there might be a Bayesian solution to that, where like if all emeralds are green, would have a higher probability or a higher prior probability than all emeralds are GRU, and so as you're updating your evidence, if you start with such a lower prior for all emeralds are GRU, most people would have that. But then Peter Godfrey Smith brought up the examples like, well, you don't necessarily have to do that. What if you'd never seen emeralds or anything like that, and you were just starting with 50-50 chance for either one? So
yeah,
it gets crazy. All of these different problems of trying to see like, what is evidence? And it's almost just like, I just know it when I see it,
Yeah, or these other, I think at one point we talked about this was Peter Achenstein had something where he had an example of, I probably shouldn't be trying to remember this in its details because I don't remember them specifically.
I'm the same way. There are so many, it's like there are so many details. It's like, I'm not going to be able to explain it right.
But something like there's two, so I think he was arguing against something like a Bayesian interpretation of evidence of like conditional probabilities.
Okay.
By saying that if something is evidence for something, then it should be a good reason to believe it. But then you could have some observation that in the Bayesian sense, it increases the posterior probability of multiple different hypotheses that are contradictory. And it can't be a good reason to believe all of those because they're contradictory. Therefore, like this Bayesian interpretation doesn't work.
Right.
I don't know how much I buy that argument, but
yeah. Well, and one of the things about a lot of these models, and I won't get into it, but like the hypothetical deductive model is another model for evidence. Like, if you have some deductive model and it and the evidence fits into that, would be deduced by your model, then that's another way to count evidence. But a lot of them have kind of either or forms, like yes or no, all ravens are black, all emeralds are green, or Bleen or whatever, where a lot of things in science aren't like that. A lot of things are more distributions. They're not either or type of things, or all X's or Y's. And it seems like a lot of those models that have received attention don't take advantage of the statistics or statistic perspectives. Not that necessarily really helps solve the problem of like what counts as evidence, because I'm not really sure it does.
It might make it harder.
It probably does. So, because like, well, so let's just like take a frequentist example, right? So you have some, and I always use like physical properties just because that's what makes most sense to me when from the day job. So like you have some physical property. Say you're trying to change the strength of a material, like you're trying to increase its tensile strength. So you make some change to its chemical composition, and you want to say, well, does it make a difference or not? Well, then you test it, and you get you test like 10 samples or something. You get a distribution, and it has a higher tensile strength, and you get the curves, and everything seems to it's in a high level of significance. Seems like there's a real effect there. Does that count as evidence, and why does it count as evidence, and what's the philosophical narrative behind that? I think that's probably kind of what you're wondering about, like with statistics and evidence, right?
Right. What's the when should you count something as being evidence for a statistical hypothesis, maybe?
Well, and maybe, that kind of gets into the whole statistic fours again, right? Because maybe one thing you could say is that if basically the p-value idea is if the distribution is well outside of the distribution of the null hypothesis, then that should count as evidence that the null hypothesis is incorrect. But there's a lot of philosophical machinery beneath that to support that view that seems not developed.
Yeah, I think one of the main points that Mayo tries to make with respect to this question is that in some situations you just really shouldn't talk about evidence for or against, but just a general lack of evidence, which is not, that's something that's not easy to formalize in a Bayesian perspective, and is easier to formalize in I guess this frequentist perspective, that if you haven't subjected something to a severe test, then you can't really say whether there's evidence for or against it or not.
Yeah.
And
which
maybe
is
that's
kind of Popperian in a way.
Yeah, I guess Popper would say, well, even if I've subjected it to a severe test, I can only find evidence against it.
Exactly, right. He would cut it off in that way, where she doesn't go quite that far.
But I think that might be that might be an interesting kind of point of disagreement about evidence is whether evidence can exist if you haven't subjected something to this kind of rigorous testing.
Yeah. Do you want to get into some of the case studies? It seems like this would probably be a good point to talk about those.
So yeah, I guess maybe the one that struck me the most that she talked about was the question of the Higgs boson, right? This particle physics question where you want to discover a particle. But with the Higgs boson, this was a weird thing, because most physicists, before going into building the Large Hadron Collider for billions of dollars and running it for billions more a year, they all pretty much believed, yeah, there's a Higgs boson.
Right.
If you asked them for prior probabilities, they would have been pretty high.
Yeah. It's amazing that we got that built, by the way, or I don't know, we as in humanity, but
yeah, it's this fantastically huge undertaking it's astonishing. Yeah.
Yeah.
And so if you're kind of approaching this from a Bayesian evidence perspective, like, okay, what's the importance of this evidence? We already believe this thing exists.
Yeah.
We've got some evidence that already kind of points towards it. But
yeah, it's like we're building a very expensive device to prove that grass is green or something that we already know. But I guess this is different, that we haven't seen the grass yet. But
yeah, it's this question, like what counts as seeing the graphs? What counts as seeing the Higgs boson? Like what's the difference between the high probability I assign to the existence of the Higgs boson before building and running the Large Hadron Collider and the similarly high probability I assign to it afterwards?
Right.
It might be a little bit higher afterwards, but like how are those so different?
Yeah.
And one way to interpret this is that, well, after we've built the Large Hadron Collider, we've severely tested its existence.
Right.
We've given the world or the universe a chance to say, no, you're wrong.
Yeah. Right. And was the particle accelerator also basically built for that purpose specifically? That was
one of the big purposes,
kind of the principle.
I think in selling it. They've obviously done a lot more with it, and the idea is to just look for anomalies that point to things that we don't understand.
Yeah. Well, yeah, I mean, that's an interesting point. And I would assume the reason, like, why most scientists believed that there was a Higgs boson was because the standard model makes many other predictions that have already been observed. And, the Higgs boson is kind of like an important component of the whole standard model. And so it would make sense that the whole theory would be correct.
But did those observations that we made based on the whole standard model, did they count as evidence for the existence specifically of the Higgs boson?
Yeah, that's it. And so that's one. Then that's kind of the Bayesian question, I guess. And then there's also there's the matter of the indirectness of the observation. So I was listening to another thing from Sean Carroll, who's a physicist, and he was talking about kind of how this all works. It's fascinating. I mean, so the Higgs boson has such a short lifetime that there's no way to detect it directly. There's just no instrument that could do that. But it decays, and it decays in what makes it difficult. It decays in several different ways, predictable ways, but several different ways. So when a Higgs boson is created, basically by particle collision, a number of things could happen with predictable frequencies, and then of course, even when you see a particle, as with pretty much most scientific instruments, you don't see the thing directly. You see the effects that it causes, which is true. I mean, in most cases, like even with a thermocouple, you're not seeing temperature rise, right? You're seeing the change in the properties of the metal and the electrical properties. But with so with the Higgs boson, basically it decays into other particles that are then detected. But those particles can be observed in other conditions too, right? So it's like a perfect example of looking at the null hypothesis in the comparison. So all these particles that it decays into can be observed in other situations, but the specific circumstance of creating the Higgs boson and the ratios at which these particles are observed and the repetition of the tests over and over again against the background data was used in such a way to convince and demonstrate that, okay, this has got to be a Higgs boson. When the particles, the fingerprint basically of these particles occurring in these ratios that they happen would be very, very unlikely to occur without a Higgs boson, basically, right? To what, 5 sigma or 7 sigma or something? It's
and the choice of those kind of thresholds is part of this is that there are known kind of inadequacies in the statistical model as they build it, right?
Right. Because you can even like the sensors can read false positives, right? For a certain particle. So these statistical flukes can occur. So
and the kind of the baseline models, I think they call them background models. They represent kind of what the world might be like if there were no Higgs boson or something like that, and that that's less well defined, and so you really want to make sure that you're really far away from that.
Yeah.
And part of this also has to do with kind of past experience. You look at there are lots of kind of detections that people talk about in particle accelerators, where they'll say, oh, here was like a 2 sigma detection or a 3 sigma detection, and then you collect more data and it goes away. And this happens very frequently. So more frequently than you would expect. If like a 2 sigma, that should only go away maybe 5% of the time. If it's really 2 sigma.
Oh, interesting. Okay, because I was gonna say like, oh, well, that kind of makes sense that if it weren't a real effect, but so you're saying the proportions are not what would be expected by the distributions.
Yeah, and so they know that it doesn't. It's not really a 2 sigma of like a normal distribution sort of thing. And so they know, okay, in order to make sure that we've really tested this rigorously, we need to set the threshold higher.
Oh, okay. Very interesting. Yeah, I would love to. It'd probably take too long for me to understand the reasoning behind that. But yeah, I mean, because I guess with all these type of tests, understanding the shape of the distribution is quite important, and you can only build a distribution with data, and if the data is what you're trying to demonstrate in the first place, that can be quite difficult. I imagine it's something related to that, where so would it not? Well, yeah, I don't even know if like a normal distribution would apply in this case. It seems multidimensional when you're
and
talking about that many events.
All I know about it is that basically this, the sigma doesn't reflect necessarily kind of naively, doesn't reflect a genuine p-value in the frequentist sense. So like you should expect more things to go away than you would are strictly implied by that signal value.
So that was the reason for going to so many
Right.
degrees of significance to go overkill, I guess. And I'm trying to remember, were they criticized for that, of going to more sigmas than where it's necessary, or?
I don't think so. I mean, particle physicists definitely wouldn't, because they know this is what we have to do to be sure. I think when Mayo talks about this example, she quotes some Bayesians who say, who sent out some message, press release or whatever, saying basically like, why is this a big deal? We already knew that there was Higgs boson or whatever. And she kind of gets her jab in at that.
Do you think that might have just been like finding randos who said something?
I don't know. It's
hard to know, like, I guess, when you're not in the.
Yeah, I'm not in the know. That it was supposedly people affiliated with some organization.
Okay.
I don't know.
Now with the so that's an interesting one. I guess just one general comment on that is that it's fascinating how theory laden would be one term to describe it, right? That there are so many levels of theory and instrumentation and interpretation behind that, it can be difficult. So I certainly, as a civilian, I guess you could say, appreciate that level of rigor that they applied to it, and I'm pretty convinced. Now, what was the Eddington experiment was quite interesting as well, and I don't remember the details because it was a while earlier in the book that I read it, but something about basically that the Eddington experiment, the original one, wasn't quite as well. The significance wasn't quite as high as would have been desired, I guess.
Yeah, there were there were problems, I think. So the Eddington experiment was one of the experiments meant to to measure the effects of the general theory of relativity. So I think, and I'm also trying to remember this and not to remember it wrong, but I think the idea was
the position of a star, basically.
Position of a star, right? There was so they had to observe this in a solar eclipse. And the idea was that they wanted to observe the degree to which light from that star was bent by the gravity of the sun. And there's all kinds of things you have to do to make sure that you can measure this correctly. But they took photographs of this, and their goal was to compare the positions of the stars and how those change depending on whether they're close to the sun or not close to the sun, and when the Earth is in a different orientation.
And we're talking pretty small margins, I think, here, right? Like they're not moving that much.
And it turns out that one of the photographic plates got misaligned and screwed up, and that it was just kind of unusable data.
Right.
And the question is, well, if I'd kind of specified my experimental procedure beforehand and said, I'm going to use these plates and like the data that comes from them, I wouldn't necessarily get evidence from that if I've got this messed up data coming from one of the plates.
Right.
But then is it legitimate to kind of throw that out?
Yeah.
In terms of severe testing or of like rigor.
Well, and what's nice is that historically speaking, we're at a comfortable distance from it where it's been verified by radio waves and other methods that are much less prone to those type of difficulties. So,
and this is one of the great things. Like you can have different sources of evidence, and that's one of these like lift off or bootstrapping sorts of things.
So it's not like reflecting on this now is not putting general relativity. Well, I guess it's okay to put it at risk, right? I was going to say it's not putting it at risk, but it's okay. General relativity can handle it.
It will be fine.
It'll be fine. But I guess the question is like, was the celebration or the perception of confirmation warranted at the time? And maybe, yeah, I guess takeaway is maybe not as much as we might think looking back on it now. And I guess what are the philosophical implications of that? Like, and the difficulty back then is like they couldn't just do another test. Like, oh, that test didn't work right, because they had to wait for the next solar eclipse. So, which would have been a ways away, I guess. So where now is we could, if we were to do that type of test and have an error, we'd be like, well, just run it again, I guess. That test didn't work right.
Yeah, and if we were running that experiment today, it would probably have we'd probably have more reliable equipment and a lot of different things that make it easier.
Right.
Yeah, and I'm not sure what to think about that particular case in terms of evidence. It's one of these.
Yeah, well, because they had didn't they have kind of a range determined, like, okay, this would be the Newtonian range, kind of like a null, right? I mean, this would be our Newtonian range of where the star would be, and this would be our Einsteinian range. And my understanding from the book was that it was kind of not really far into the Einsteinian range. Like, somebody might be able to argue that Newton was confirmed.
Mm-hmm. And if I remember correctly, and this might be right, that if you left the bad data in, you actually got kind of the Newtonian answer.
Oh yeah, I think you're right. Yeah. Right.
And so that looks suspicious, and maybe it's a good heuristic to just say, okay, something that looks suspicious like that, we're just going to have to wait. Exactly
right. I mean, because we know in hindsight that, okay, they took this as confirmation and they were right, but yeah, maybe in the future when we see these type of results, we have to wait. Repeat. Don't pop the champagne just yet.
So I don't know. Did you have anything else to say about this particular case?
The only other thing I was going to say was I think she made kind of a Bayesian point about Einstein's famous thing where, like, what if the data refutes your theory, and Einstein says, well, so much worse for the data, the theory is correct. Which sounds very Popperian, an anti-Popperian, which is funny because, like, logical positivism kind of was inspired by Einstein. It's like, wow, this is what science can be, where you can make a prediction and go out and test it and falsify it, and where Einstein was a little less so himself, right? But
he just had very strong priors.
He had very strong priors, and perhaps justifiably so. It was very well formulated. So, yeah, I mean, should Einstein say the Eddington experiment had come out the other way, or if they had interpreted it the other way, should he have said, "Oh, I guess I was wrong"? Maybe not. Maybe not. Well, I guess not, right? Because he was right. We're pretty sure now that he was right. So, and that's an interesting consideration of how to weigh evidence, and to consider falsification, right? That maybe it's not always as simple as, like, maybe the test you set up that you thought would be conclusive, after the fact you realize wasn't, and it seems like really sketchy to say, oh wait, let's change the test, but it could actually be legit.
Yeah. And then on the other hand, it's also kind of sketchy not to change it if someone, like, what if you had been trying to disprove general relativity and you leave in the bad data?
Exactly.
And I think, yeah, that this is one of those, yeah.
It gets into replicability, right? Because, I mean, for a lot of tests, we're not limited to testing them only once or twice. We can test them over and over again. With certain cases, that's not the case, but most tests we can do that. And so if it's still an open question, you can keep doing it. Although I guess that's money, but what's a couple billion for a Large Hadron Collider between friends?
Exactly. So there's another kind of example that's like this, again, where we know the answer now, and that's discovering that smoking causes lung cancer and a whole panoply of other diseases. Right. I
knew you were going to talk about this, and I was driving today. I was thinking, what if cancer causes smoking? I was like, that doesn't even make sense, but it made me laugh.
So Fisher, we talked about him briefly. Actually, he was by the time that people were really kind of talking about cancer and smoking as something that was a problem. He was kind of the old curmudgeon who was trying to argue against all of this stuff and pointing out all of the statistical flaws.
Oh, Ron,
and in fact,
the old curmudgeon.
And in fact, in a paper, he in fact raises that possibility.
Nice.
He basically says that, well, maybe people with like precancerous polyps in the lungs have kind of you seek out tobacco as kind
like
of
to soothe it or something.
To soothe it, right?
Yeah.
It's not clear how serious he was about that particular one. He was more interested, I think, in a third possibility where both cancer and smoking are caused by some third.
Like some genetic proclivity or
genetics.
Something. Yeah.
Specifically. So he said that people who are genetically inclined to smoke are also genetically inclined to get cancer.
Well, and and also I don't know what Fisher's motivations were, but there's also kind of the principle of the thing as a general philosophical principle, right? It's like we need to have some type of way to distinguish the order of causation, right? And this is a good example to work that out,
and so this is maybe one of the earlier questions in philosophy of statistics that I was interested in a while back. I read some of the papers from the time. There was a paper in the late 50s that was kind of intending to rebut a lot of these objections that people had made to the hypothesis of smoking causes lung cancer. And they tried to assemble all of the different lines of evidence that they had at the time that indicated that this was an issue, and give responses to different objections, including Fisher's kind of, is this genetically caused rather than kind of environmentally caused question.
Yeah.
But yeah, the question of how have you, at what point should you have concluded that smoking caused lung cancer?
Right. Yeah.
Because the evidence started out kind of spotty, and you kind of had some doctors noticing, or you had these very small kind of case studies where you look at, well, I've got a couple hundred people with lung cancer, and I'm counting how many of them were smokers, and then I try and match them with people in the general population of the same age and sex, and kind of just fit them together who didn't have lung cancer, and now you say how many of those were smokers, and it's interesting, but I don't know how demonstrative it is,
right?
And you can't ethically run an experiment where you're like, tell people to smoke or not smoke, and then see 20 years later how many of them have lung cancer,
right?
So these questions of statistically inferring causality in medical settings are tricky.
Yeah. And I mean, you talk about how it's like we didn't know then, but we do know now, which I mean, I don't disagree with, but like, why do we know now? Like, what's the difference?
Right. Yeah. That's a really good question. So some of the different lines of evidence. So these kind of retrospective studies are easy to like argue against. You might say, oh, well, maybe like people who don't smoke that get lung cancer die so much more quickly that you never observe them, and you only see the smokers with lung cancer because smoking helps them survive it better or something like that, right?
Yeah.
But okay, so you can answer that by doing a different experiment. You can register people beforehand where none of them have lung cancer, at least as far as you know, and you follow them along through 20, 30 years, and you watch how many get lung cancer from each group. And in fact, there was a really long-running study of British doctors that did this over a period of 60, 70 years. So there were multiple cohorts that went in, and this was one of the big kind of convincing pieces of evidence where you look at this and say, oh, there's a really there's really a much higher rate of lung cancer among the smoking doctors than the non-smoking.
Mm-hmm.
And that avoids some of the problems. It doesn't necessarily establish causality, but it's very kind of suggestive.
Yeah.
Correlation doesn't imply causation, but sometimes it can just it can really kind of point a finger or wink suggestively, at least.
Well, and I don't know if this has been done, but because I was reading a little bit about this, and I thought, well, what about people who stop smoking? Has that been an avenue studied? Like, if some people who continue smoking throughout their life versus people who smoke early in life and then stop, and what are the cancer rates with them?
Yeah.
And so I know nothing about if that's been done, but
and at this point, yeah, I would say that probably any experimental construction that you can think of about smoking has been done. I mean, there's people who've done studies on like third-hand smoke.
Yeah.
So, but
well, I guess in terms of severity testing, big tobacco, if I could use that word, has probably done everything they can to try and disprove or to prove the null hypothesis, right?
Yeah.
And disprove that
exactly.
hypothesis.
There are other things that you can look at, maybe like biological mechanisms.
Right.
So some of the earlier evidence was from people basically trying to get cigarette smoke to cause cancer by and these are all terrible things to do to animals, but you take condensed cigarette smoke and paint it on the ears of rabbits or whatever, right, and see if they get cancer. And this was something that people could nitpick at. You could say, well, the smoke that you're using was combusted at a much higher temperature than actually occurs in people who smoke, and so you have to go back and do that experiment again and kind of show that chronic exposure does this and this and
right.
And so there's in part, this was kind of the result of maybe a decade-long conversation between people who said, oh, this is really worth looking at, and we think that this is something going on, and then other people pointing out flaws and trying to respond by finding other experimental evidence you can do. The American Cancer Society actually originally did one of these big cohort studies trying to prove that smoking didn't cause cancer.
Oh, interesting.
And then they changed their mind.
Okay, nice.
So,
that's a good way to do it.
Yeah, this was I think 1954.
So mechanism and theory seems important. And I was listening to a podcast called The Filter with Matt Asher, which I think is a statistics podcast, but I was listening to it because Deborah Mayo was on it. And he was kind of throwing out the idea to Deborah Mayo, could you just not worry about theories or mechanisms and just look at models as black boxes, like inputs to outputs? And Mayo was like, I don't like that, because if you want to be able to affect reality and change it or improve it, you kind of have to know what's going on under the hood and know what's happening. I mean, I am definitely, I like black boxes as better than nothing, certainly. But I also think that having more detail of the inner mechanism is generally better. And this seems like a good example of that, where especially in biology and in neuroscience in the future, as we learn more about it, that as we start to see okay, how does it happen, right? Not only does it happen, but how would it happen? That can help also with the causal inference.
Exactly.
Okay, not only do smoking and cancer correlate, but we have an understanding of why smoking causes cancer and what's the actual anatomical and chemical process that leads to it. And in a way that's almost like a theory of evidence for me as well. It's kind of like a narrative evidence, where it just makes a plausible story,
Yeah. And there's in the context of maybe epidemiology or these sorts of medical things, there's been a lot of thought put into this, right? Because you can't do the same kinds of randomized experiments that you often can in other settings to establish causality.
Mm-hmm.
So you really do have to think about the models,
Yeah.
and just the kinds of what should we expect to see in a situation where causality is happening.
Economics seems like a place for that as well, right? Because you can't do, a lot of times you can't do controlled experiments.
Yeah, and there's lots of clever things that you can try, and they're of varying degrees of convincingness. And yeah, that's all. Causality is hard, but I mean, it's clearly an important thing to answer. Like the question of whether smoking causes lung cancer is a very important question, and getting the answer right on that and getting the right answer as early as possible is something that.
And it seems like an important thing of science as well. Like there are these different levels of the scientific enterprise, and one is gathering evidence, but then there's also, I would say, explaining. An explanation is another field in the philosophy of science. It's like, what does it mean to explain something? And that kind of takes us afield. But that's something like I want to know, So like, so Newton, for example, that was, I think, something that bothered him, was this action at a distance. It's like, okay, I can see planetary motion, but I don't know why it happens. Like, why would the planets move in that way? I can write the equations, but I have no idea why it happens. And I think he was bothered by that, if I remember correctly. And I don't know if we ever like really get to a point where we completely explain, but it seems like we kind of keep pushing further back. So like with general relativity, I think it explains part of it, but then there are new questions, right? So the curvature of space-time explains the action at a distance and why objects move in the trajectories that they move. But then that kind of brings up the questions like, well, okay, but why does a mass energy cause space-time to curve? So,
right. You answer your questions by replacing them with more incomprehensible ones.
But exactly. Well, I was going to say it's progress, but now I'm not so sure. But I think it's still progress. It gets more difficult, right? It becomes more, the hurdles, rather than saying it makes them replaces with more incomprehensible, the hurdles to the next step are a little higher.
Yeah, your abstractions, you've kind of, I'm not sure how to say this, but you're building layers of abstractions, and your previous abstraction that was a black box, you've built one inside of it.
Right. Yes.
You
that's
know
a good
more
way
about
of
the inner workings.
Yeah. And it's like sort of black boxes all the way down, but you start seeing that black box is moving as gears. Yeah. Okay. Good. Okay. So we talked about induction, evidence, mechanisms. We've been going for a while. Do you want to? Do you have any more that you want to touch on?
I don't know. I think I've talked about a lot of the things that I wanted to talk about.
Good. I'm glad.
Let's see.
Let me just hit on a few that I had, because I want to take the opportunity to bounce some ideas off you. So one thing that I've been interested in, and sort of in the context of quantum mechanics and quantum properties, but not just that, is this idea of like, okay, what is the object that we're ultimately after? So it's interesting to me how distributions come up all the time, even in classical cases, where one way to think of it would be as like imprecision. Like, okay, there's the real value, and then we just have all this error. So that's one way to look at it. And that the probability distribution is kind of obscuring the thing in itself, which is kind of a very philosophical Kantian way of looking at it. Where I kind of am thinking, well, in a way, you could look at it another way and see like, okay, the distribution is the thing, and there's a lot of information content in it, right? So it's not that you're looking for this single value and trying to get through the haze, but that you want the full picture, and that is what you got. And you could take a mean of it and say, okay, you know, for shorthand, we'll call it the mean. But and I don't know, what do you think of that of that type of outlook?
Yeah, it's a part of the question of, you know, whether something is maybe intrinsically random or intrinsically stochastic versus due to some lack of information that we have. Right. So and in the quantum setting, there are theorems that show that, you know, there's no way for it to just be by lack of information.
Exactly.
Right? There's no hidden variable way of explaining the results that we get. Yeah. So is the distribution the thing? Apart from maybe a quantum perspective, I'm not sure that it is. Every you know, once you get above that quantum level, like every distribution is in some sense representing our inability to actually know all of the state of some
system. Well, yeah. So let me think of it this way. So say like you're looking at some classical level system. So like let's take kinematics. So we're looking at the trajectory of some object in a gravitational field. That should be highly repeatable. Say we're doing it in a vacuum. We do everything we can to make it very, very replicatable. But there's still some variance. Now, I think it's probably true that, like, say the object is supposed to land or hit this point at this velocity, and it's a tight distribution, but it's still a distribution, and we can chalk that up to just imperfections in our equipment, you know, that is non-ideal. I think that's true. That it's the distribution is not because there's imprecisions in the physical law, but that it's related to other factors that we just can't account for.
Yeah. So I think one thing that makes this that is maybe evidence for this is that we can build progressively more precise measurements.
Yeah.
Measuring tools. Right?
We're not hitting a limit. Based on.
Yeah. And I mean, there is a quantum limit. Like we have Heisenberg uncertainty.
That's a good. Yeah. That's true.
But like at the classical level, at the levels where we can maybe see things, that's not, you know, that doesn't happen. We're able to build very, very precise, like we can build electron microscopes,
right,
and manipulate things, move things on levels where that's, and there's not, so there's not maybe a good reason to say, well, I don't know, like there's.
I'm thinking of changing. So like, rather than saying like the distribution is the thing, is more that there is what you have are data points, right? So like to use my velocity example, you have the velocities, and those are what they are, right? It's not a distribution; those are individual data points. But it can be useful to have the full data set still, because for whatever reason, if you're engineering a device or something, you need to know that distribution. So you want that information-rich data set. But yeah, I think I agree that it's in some type of metaphysical sense, the distribution is not the thing in itself, but it's a collection of elements.
Yeah. So I mean, there's an interesting maybe Bayesian versus frequentist thing here in that if when you're one thing that people say is at least that for a Bayesian, the data is fixed and maybe the parameters of your model are random, whereas for frequentist, the data is random and the parameter is fixed. You just don't know what it is.
Right.
And yeah, so from that perspective, One of those is Bayesian, one is frequentist. But
yeah, that's an interesting point.
I think distributions, you can use them in two ways, right? You can use them to compress kind of a large amount of discrete information. As I've sampled a lot, and this is kind of how it's been shaped. Or you can think of them as generating kind of things that are that you can observe, but do not exist beforehand, maybe.
Yeah. Okay, that's a very interesting
those
point.
Are maybe, and mathematically those are kind of equivalent, but philosophically they're not.
Right. Another example I think of, and this one I think is fundamentally random, is but something that fascinates me. So like radioactive decay, I believe is understood to be fundamentally random. But over multiple events, there's a predictable pattern. So you basically you have an exponential decay function with the decay. So you can have a half-life, right? And know at what time half of the decay will have occurred, and that's a predictable pattern. Even though and it's actually because of the randomness that you get that pattern, which is kind of cool. So is that because of some intrinsic property of the material, which it kind of seems like it would have to be, or is that something that we just observe this effect? The reason I would say it seems to be an intrinsic property is because we can say of different aliquots of material that we always get this. Carbon-14 always has the same half-life no matter where we got it from or whatnot. But yeah, the curve, I guess, is generated by specific events.
Yeah, our observed curve. And so this is right. So if your data was generated from one of these processes, you observe it for long enough, you'll replicate the same curve. And that's kind of the law of large numbers.
Right.
A lot of different kind of statistics theorems. But so in some situations where you do have this intrinsic randomness that's coming from quantum mechanics or whatever, then one of these models, I think we're fairly confident is the right way to think about it. But then on the other hand, if you're thinking about maybe polling people in a population, there's a distribution of heights in the population, but it's not. I mean, it's not a random variable. It's not something that that's generating things. The people are there, and you're describing it kind of concisely by using a distribution function.
Yeah. I like your point about how it's compressing information, right? Because you can discard all the data in the data set and just replace it with that function, which has less information, but generates the similar results. One other question, and I think this is something you mentioned as well, is kind of at the heart of all of this is what is probability and what is randomness. So like what does it mean to say that something is random?
Yeah. And the mathematician's answer to that is, I don't know, shut up and compute.
Right.
Because I mean, you can do tons of really cool math with probability without ever saying what it is philosophically.
Yeah.
And that's great. But then this is maybe the subjectivist versus objectivist, Bayesian versus frequentist, kind of the source of everything is, right? Are probabilities properly representations of degrees of belief or uncertainty, or are they really just operationalized by long-run frequencies of repeatable events or experiments?
Right.
And so one of the things that's interesting. Okay, so maybe one of the canonical like frequentist probability things is, okay, if I roll a die, probability that I get any one of the numbers should be 1/6. But it's not obvious why that should be the case. And you could build a robot that rolls a die and always gets 6.
Yeah, I think there's actually a robot that has been built to flip a coin that always lands like on heads or something.
I understand, like, if you've got a steady hand and you practice enough, you can do that. Yeah.
Right. Yeah.
And so this question of, like, even in these kinds of canonically frequentist things, there's some aspect of this lack of knowledge, and like we're deliberately hiding some information from ourselves and hoping that produces something that in the long run has these properties.
Yeah. A lot of it, so I think at the macro scale, well, I was going to say at the macro scale, everything seems to be pretty not fundamentally random, that it's more like an epistemological question, right? That we just don't have all the information. And that can be pretty extreme, like with chaos, right? Where chaos is deterministic, but just tiny differences in initial conditions will make it unpredictable for all practical purposes, right? But it's not like metaphysically random, whatever that might mean. And where we get into the fundamentals, right, is at the quantum level, right? There are still different interpretations, and that sort of overlaps with my question of what is the thing, right? And so what is an orbital? Is an orbital what the electron is at when it's doing its thing, when it's in the atom, or is it a probability distribution of finding an electron in a certain location when it's detected? And there's kind of a shut up and calculate element to that as well, but it's also one of those things we kind of want to know. And a few points on that. So one, there is an interpretation of quantum mechanics that is completely deterministic. So there's the many worlds interpretation, which is that basically all of the components of the distribution are realized, and that there's no wave function collapse, and that there's just this basically incomprehensible multitude of all the possibilities being realized in what we would understand as a classical sense. Another thought, and I don't know how I feel about that, but another thought though. So so orbitals are interesting, and I like to think of orbitals mostly because of the chemistry, and that's where we see these type of functions the most. Is the wave mechanics of it. So and basically the tying of the momentum to wavelength, to wavelength has very interesting and unique implications for quantum mechanics. But outside of that, even just in wave mechanics, the inability to specify a time domain and a frequency domain to precision is just an aspect of waves generally, right? And when we're talking about classical waves, it's not really something we would expect, right? Or no, sorry, we wouldn't expect anything different, right? So if you have a pure sine wave, you look at that and be like, well, of course it's not localized in space. That's just, you wouldn't expect that of a sine wave. That's not the type of thing that it is. Whereas if you're trying to get a pulse and you're doing a Fourier series and really localizing it and getting a ton of wavelengths superimposed upon each other, then yeah, you're not going to be able to specify the frequency when you're localizing it in the time domain. That's just what the way waves work, right? So you wouldn't expect anything differently. And particles being waves, we see the same thing, right? But the tricky thing then is that wavelength is tied to momentum. So then it has this weird, unexpected result that we're not able to localize momentum and position at the same time, which seems very strange. And I guess but part of that, tying it back to waves in general, it's almost like, is that just because we're just expecting something of it that it doesn't make sense to expect of it, you know, by the nature of the thing that it is? It's a wave. So yeah, it's momentum too, but I mean, I guess in a way I'm trying to make it seem less strange. But
yeah, no, I think that's a really a very good way of thinking about it. Is the weird part is not that you can't localize it in both bases at once. It's that one of these bases represents position and one of these represents momentum.
Right, which is a classical concept.
Right,
and that we observe, right? When we collapse the wave function, we observe them as classical entities. But
exactly,
and that's what's weird. And
yeah,
right, because in a normal wave you don't see that, right? It doesn't break. It doesn't collapse into a classical or a non-wave property, where with an electron it does. And I guess that's what's strange about it. Yeah. So, and is that fundamentally random at basis? I mean, it seems to be.
Yeah, it's maybe fundamentally more than random.
Yeah.
in it, or more random than random. In certain quantifiable ways. Like,
right. I mean, it depends what we're talking about, right? Because if you're talking about the evolution of a wave function, that is determined. But it's what level you're looking at, right? If you're looking at the level of the whole wave function itself, that's deterministic. But then if you're talking about like some specific classically observable event and trying to predict when and where it'll happen, then that appears random from that standpoint. But,
yeah. And you can get random behavior that you couldn't from just actual kind of classical randomness.
Exactly. Yep. Exactly. Yeah. I don't know what else to say about that, but it's but it's interesting. Well, and it's a statistical interpretation, right? So like with and so it relates to the philosophy of statistics with the Born interpretation. You know, they were kind of trying to figure out, okay, what is this wave that we're talking about? And the only way we're really able to interpret it is like, well, if you square it, it's a probability. You know, and that's the way we talk about it.
And you know, one way to try and maybe like cordon off all of the weirdness in quantum mechanics is basically to say the only time we're allowed to talk about quantum properties is when we're performing some experiment.
Yeah.
And we have some well-defined starting position and some ending position where we measure things, and the kind of quantum mechanics is just rules for telling us probabilities of things that we might see on the output.
Very good. I'm just looking over our list. I think we've definitely touched on most of the main things we were interested in. So, are you still interested in philosophy of statistics, or has this totally like?
I think I need to read a Bayesian now. I think.
Yeah, well, you know, and I was realizing as I was talking with Jared yesterday, I was like, I really do want to understand, like, you know, its best case. You know, I don't really know how to use it in the ways that it seems like people want to use it, except in like engineering applications.
Yeah. So a long time ago, at the recommendation of a professor, I got Leonard Savage's Foundations of Statistics. So he's a Bayesian, and this is a book from like the 60s.
Okay.
And he starts off very Bayesian-like and starts with like utility functions and decision theory. And so it was an econ professor that recommended this, and this was like right up their alley.
Yeah.
And I never read past that part, but I looked at it a little bit more, and he has some really interesting stuff. So he recognizes this problem that Bayesians have with the subjectivity of the prior, and tries to give some kind of Bayesian-based ways to do statistics without priors.
Okay.
And so he has this kind of minimax, he calls it, formulation, where and it's not his original idea. I think it's from Abraham Wald that started this. But the idea is basically you are playing a game against the universe, and you're trying to, no matter what the universe does against you, you're trying to minimize the maximum like error that you could have.
Right.
And And so this doesn't require a prior probability on what the universe is going to do. You just kind of like you're trying to just kind of loss avoid, maybe.
Yeah. It makes me wonder, like, and I think we're both kind of, expressing that we're not like anti-Bayesians or anything like that. But, is there like, would it even make sense to wonder like which one is true? Like, or to definitively prove one right or wrong? I mean, how would you even do that? I don't know that that's possible.
Yeah, I mean, in some ways, like both of them have theorems, right? And
right.
like those are deductively true, and and in fact, those theorems are operationalized in certain ways in terms of like you can in the frequentist setting, you can make guarantees that, I mean, no one ever fulfills all of the hypotheses of the theorems, but if you did, like you would have these guarantees about long run behavior in the limit.
Right.
In the Bayesian setting, you'd have these guarantees about consistency of your kind of computed posterior distributions, and probably some other things as well that you can get. So in some sense, like they're both true, or there are things about them that are definitively true. Beyond that, I don't know.
Yeah, I had proposed like am I a hammerist or a screwdriverist?
Right.
To take a simplified example, it's like, well, it depends. I mean, I use both for different things. But
it depends on what theorems you want to be true, or to be able to use.
Yeah. I mean, and it almost seems like I wonder if part of it's like there's statistics wars with like your Fisher and Neyman Pearson people who just have some bad blood for whatever reason, and maybe there's a lot of statisticians who are like kind of on the sides getting together on weekends and be like, I don't know what's wrong with those guys.
Right.
Like everyone, I like to think the rest of them are just kind of like, yeah, we all get along. Just do things in slightly different ways. But.
Yeah, I think they do. It's probably more the philosophy of statistics people that really kind of get on each other's cases.
Yeah. Good.
But to do statistics, you need a little bit of philosophy. So
absolutely, yeah. Like, what are we doing at the end of the day? What does this all mean? Excellent. So
did we solve the statistics wars?
I hope so. I hope that when they get to the end of this 2.5 hours, that they will have come to an accord, and we'll sit down together and sing songs and bring the millennium and all that stuff. Well, cool. Well, thank you so much for taking the time to come on. I hope you enjoyed it. I mean, I know it's a topic of interest for you, so
definitely.
It wasn't a huge sacrifice taking the Saturday evening.
No, this was lots of fun. Yeah, thanks.
Good. All right. Well, I'll talk to you later.
Yeah, see you.